Yeah, sorry.
So once again, welcome to this second part, and hopefully we can conclude that session, the entire session, oxidation reduction session. I know this is going to be it's a tough task for you to complete the entire thing in 2 sessions, but I'm sure that students will greatly benefit from this session because getting all these reagents in a very systematic way that is not seen in it. It's very difficult to get such a class, especially for students. It's totally distributed in different chapters. There is no like a systematic way of approaching oxidation and reduction part. And most of the things, these are all direct questions which can be seen in GATE and CSIR and JAM question papers. So definitely students will be greatly benefited. And we are recording all these videos and we are sharing with the students and other who could not join. Uh, Many students have asked us to do that because they are having classes and even at 2:30, 3:30 time. So we are uploading that on YouTube and many are watching it. You can see from the news, many students and from not only from Kerala, from other states also making use of it, and we are extremely happy that. And and getting good, excellent resource persons like you is really great for our program. So once again, welcome back, Professor Biju, and all the teachers and students to the second session. We will conclude this session, and please feel free to ask question in between if you have. No need to type in chat box. You can directly unmute and ask question in between. So if you are just typing in chat box, it's difficult to see that. So you can ask questions that you please use. And next week we'll have uh, organic chemistry, especially on molecular orbital approach to organic chemistry, focusing mainly on pericyclic reactions and aromaticity and so. Uh, in fact, the orbital thing, it's totally a scary thing for many of the students. And hope next week we will cover that, Tuesday and Wednesday. So, okay, we'll start today's session. Okay, over to you.
Okay, so 1 second. Okay, so Joman, can I share the slide?
Yes.
Okay, good. Is it visible?
Yes, it's visible.
Okay, good.
Yeah.
So it is fine, right?
Yeah, it's fine.
Yeah. So welcome back, all of you, once again. Yeah, I know it is equally difficult for all of you to listen to this 2 hours organic chemistry talk, but I will try my best to, what to do. So I will try my best to make it a little attractive. And in the end, I'm sure that you will get some take-home message at the end, which will help you to clear some of this competitive examination, just as Joman indicated. Good afternoon to all of you. Yesterday we discussed about one phase of the reactions in organic chemistry involving the reduction in organic chemistry, where a flat molecule is converted into a tetrahedral molecule. And today we will be discussing the reverse thing. We will be discussing about mainly on oxidation reactions, how we can convert the oxidation of various compounds, converting a tetrahedral molecule to a flat molecule. So before we start, I would also like to discuss a few more things about reduction reactions that we were not able to cover yesterday. So we have been we've discussed about the borohydride reactions yesterday and the borane reaction yesterday. And we sort of know that there is a difference between borohydride and borane. The difference is borohydride is a nucleophilic reagent, so the BH minus can add to various nucleophile, whereas the borane reagents or simple boranes are electrophilic reagents, where these are mainly electrophilic, where a nucleophile first has to add to the borane, making the boron tetrahedron, and then the hydrate transfer take place. A typical example, what we discuss, I'm showing the use various functional groups. So if we have a molecule, say specifically a pyridine non-containing compound having an ester moiety and an amide moiety, and we know that this borane reducing agent, it is electrophilic, so it will add to the more electron rich center of the functional group. So if you take an ester and amide moiety, the amide, because of the presence of the lone pair of electrons on nitrogen, this is relatively electron rich than the ester moiety. So the borane can be coordinated with the oxygen of this amide better than the oxygen of the ester, which leads to this ylide type intermediate. And once this ylide intermediate is generated, so if I write this BH2 and H, this hydride can be transferred in an intramolecular fashion, leading to the formation of this species. So that is the replacement of one of the BH bond of borane. And now we have two more hydrogen like that, so two more boron hydrogen bond. This can again do the same process, leading to the replacement of all the three hydrogen atoms of BH3 by this species, which is a boric acid derivative. And this boric acid derivative now can hydrolyze. And in the end, you get H3BO3, which is boric acid in the end. And the remaining part, 3 times, because this process happened 3 times, you get an iminium species. And this iminium species can be further reduced to an amine. So in the end, what happens is we reduce a lactam derivative, a functional group containing a cyclic amide moiety, to an amine moiety where the CO double bond is converted into CH hydrogen bond. And we also know what are the difference between borane and borohydride based reducing agents. The differences being one is electrophilic reagent and one is a nucleophilic reagent, and also the mode of addition. So one of the most and perhaps the remarkable application of borane is in the application in Reagio Selective reduction reactions. If you remember yesterday we discussed the reduction reactions. The important aspect of reduction reaction is we convert a flat molecule to a tetrahedral molecule. So if you consider the reduction of a ketone to an alcohol, we convert the sp2 center to an sp3 center. And if we have different groups attached on the ketone, at the end of the reduction reaction, we get a chiral center. And if we use a chiral reducing agent, we can have Reagio Selective construction of the desired product at the end of an in-ensure selective reduction reaction using borane. And one such reducing agent, which is very common in organic chemistry, is the use of chiral boranes. And specifically, this type of catalyst, the chiral oxazoborolidine catalyst, which is otherwise known as CBS catalyst, the Corey-Bakshi-Shibata catalyst, which was demonstrated very long back from Harvard University by Corey group. So the idea is this catalyst can be of this reagent can be of two types. In one way, this is a chiral borane reagent where you can have a BH bond where this BH bond can be donated to the substrate, where you need to use this reagent in stoichiometric amount because it cannot act as a catalyst. On the other hand, if we protect that BH with a simple methyl group, along with an additional supply of a borane, a diborane or any other borane source, this oxazoborolidine can act as a catalyst in various reduction reactions. So that is one of the important application of the CBS catalyst, Corey-Bakshi-Shibata catalyst, because of the nature of this catalyst, which is it is having a chiral center. Because of the chiral nature of this catalyst, which the catalyst can release the hydride from a specific phase of the molecule. So we know that the ketones are planar molecule, so or aldehyde or a ketone, wherever you consider, these are flat molecule. So if we can discriminate the two phases of a ketone or an aldehyde using a chiral catalyst, what we can do is the selective hydride delivery can lead to the formation of the alcohol with precise control over the resulting stereochemistry. So this type of catalyst, the CBS catalyst, can be prepared from a chiral approach starting from proline. And we can see this is the chiral center in proline. And if you take proline and if you add a Grignard reagent, say for example, phenyl Grignard, and I'm sure you are all aware of what is Grignard reagent. So the Grignard reagent will add to the carboxylic acid. So two equivalents of Grignard will add to form this amino alcohol moiety. And to this amino alcohol moiety, if we add any boron source, because of the electrophilic nature of boron, this NH and OH can coordinate to the central boron species to form this catalyst. So in this case, it is a boroxine which is used to generate this catalyst, which is very much stable. And since the catalyst does not have a BH bond, which is responsible for the reduction reaction, one has to use stoichiometric amount of BH3 in this reaction. So what essentially happens is when you add the CBS reagent to borane, diborane or whatever, or any reagent, a borane THF complex that we have seen yesterday. So the lone pair of electrons can add to the boron, generating this intermediate. Now this boron is negatively charged because the lone pair of electrons from nitrogen has been transferred to the boron. And now it is as simple as saying it is a borohydride equivalent because the boron is negative charge. And then subsequently, if we have a ketone substrate, the ketone substrate can bind to the boron, again, the boron which is not coordinated because of the lone pair, the electrophilic nature of boron and the ability of the oxygen lone pair to coordinate to the boron, resulting in the formation of a rigid intermediate like this, where the stereochemistry of this oxazoborolidine will determine the selective hydride transfer from this intermediate to the aldehyde or a ketone. So in this case, the because of the nature, because of the stereochemistry of starting proline, the delivery of the hydride always starts from or takes place from the top phase of the molecule, because the bottom phase of the molecule is blocked, and this leads to the formation of this intermediate, which on hydrolysis will lead to the alcohol, which is enantiomerically pure in form. So we can use this method for the enantioselective construction of chiral alcohol from a carbonyl compound. There are two ways. One can also use the stoichiometric amount of this oxazobororidine reagent, where there is a pH bond which can selectively donate one of this hydride. Or in other words, one can also think about the CBS catalyst, where the boron is protected with a methyl group in combination of an external source of boron, so a borane source. And this is a cycle for how to convert a carbonyl compound into a hydroxy compound or an alcohol via the coordination between the amine to boron and the boron to carbonyl compound to get this intermediate, where the hydride is selectively transferred from a single phase of the molecule to form the chiral alcohol. So this is something we missed out yesterday. And with this, we have covered almost all important reducing agents in organic chemistry, especially based on the hydrogenation concept, the reduction reactions. And one more important area of reduction reaction is how we can do a reduction in the absence of any metal. So we can also do, so most of the cases we use this metal-based reducing agents starting from sodium borohydride, and we have seen the borane-based reducing agent. But in some cases, we can do this without the assistance of this hydride source. What we can do is use the ability of elements like sodium or lithium, and you know the remarkable property of this alkali metals, because it is very free to donate the outermost electron. And we also learned yesterday that we can hydrogenate an aromatic compound, a planar molecule, to a completely flat molecule, say for example benzene 2-cyclohexane derivative, using either the heterogeneous hydrogenation strategy, what we have seen, or we can also use a Wilkinson catalyst in presence of high pressure of hydrogen. However, these methods, the hydrogenation techniques, are having a drawback that you cannot have a control over the stoichiometry of the hydrogen gas use. So whatever hydrogen double bonds are available in the substrate, everything will be reduced in the presence of hydrogenation condition, so that an aromatic system will completely convert into a saturated system. Suppose we want to construct a cyclohexadiene, for example, from benzene. So what is the method to do that? So to convert a benzene molecule to 1,4-cyclohexadiene. So the method of choice is what is known as a name reaction, Birch reduction. The reagent normally people use is sodium and liquid ammonia. So liquid ammonia means you can imagine at what temperature one has to do the reaction, because at room temperature ammonia is a gas. So liquid ammonia means the ammonia will boil at -33 degrees Celsius. So the reaction has to be carried out below -33 degrees Celsius. And one need to have a source of hydrogen and alcohol, which is essentially the source for the saturation of this benzene derivative, and the hydrogen source is this alcohol or a protic solvent employed for the process. So the solution of sodium in liquid ammonia, so what will happen is that we know that ammonia is a very good ligand, and we also know that sodium metal has a probability or the remarkable ability of sodium or any transition metal to donate the outermost electron. So this two combination will lead to the formation of an electride salt, a salt of sodium ammonia with a free electron, which is donated by the metallic sodium. So this leads to an intense blue colored solution, and this is otherwise known as a solvated electron. That electron eliminated from sodium, which will be available for addition across various compounds. So this electron can freely add to aromatic system. So whatever electron ejected from sodium, so if you see sodium metal, so this can be considered as an electron, and then Na will convert into Na plus. And this electron ejected can add a homolytic way to the aromatic system, thus generating a radical anion. So because of this polarization, here we get a negative charge, and here one electron transfer takes place. So this electron will be here as a radical and an anion. So we get a radical anion. And this radical anion will capture a proton. So this negative charge can easily capture a proton from the alcohol solvent, converting this into a radical species. And this radical can accept one more electron from a second molecule of sodium, converting to, so this is already one electron here, and another electron will be attracted because the sodium will donate a second electron, will convert into an anion because the second electron will make this radical an anionic species, and this anion again can accept a proton, or getting it converted into 1,4-cyclohexadiene. So this is a mechanism of a Birch type reaction. So the most important aspect of Birch reduction is that, so if you look at any sort of hydrogenation reaction, whether it is homolytic cleavage or homogeneous condition or heterogeneous condition, the benzene molecule will be converted into cyclohexane molecule. However, if you want to convert benzene into partially to a saturated system, or reduce benzene to saturated system by any method, so if we cannot apply the normal hydrogenation conditions, but the method of choice is the sodium or lithium also one can use in liquid ammonia in the presence of a proton source. So everything worked fine as long as you have no substituent in benzene ring, because the ring is very much symmetric in nature. However, the important aspect of this Birch reduction, this is something very frequently asked in CSIR and GATE exams, is the Regio Selectivity. So if you have a benzene ring with an electron releasing group, say for example anisole, so if you have anisole as a substrate, and if you do a Birch reduction on anisole, what will be the product? So we know that at the end of in the Birch reduction, in all the reaction, an electron adds to that aromatic system and generating a radical anion. So the Regio selectivity in this addition will be determined by the group present. So for example, OMe, if in the case of anisole, we have OMe. So OMe, we know that electron releasing group, and when we add an electron to this type of system, the anisole derivative, we have to make sure that the radical anion, so once we add an electron to the system, say suppose we add an electron to the system at this carbon, okay, and then you will be generating a radical anion like this. So the only thing we have to remember is that if you have an electron releasing group and the carbon carrying that electron releasing group with a negative charge will be highly unstable, because this electron releasing nature of this OMe will increase the electron density of this carbon, thus destabilizing it. So if we have this type of electron releasing group on benzene ring, the electron addition will take place in such a way that the negative charge should not be attached to the carbon bearing the electron releasing group. So that means if you think about the addition of an electron at this carbon, so we can have this type of polarization. You get a radical anion, and this radical anion gets protonated. The second electron adds, making this anion, and you get the product. It does not have to be necessarily here. The electron can add here also, so that it can be polarized in the opposite direction. So either of the meta position, one or the other meta position, can have the addition possibility to generate this radical. So earlier it was here, now it is here, and the protonation and a subsequent electron transfer generate an anion which can be protonated to form this product. So in the case of electron releasing group, it is very important to note that the negative charge should not come to the carbon attached to the electron withdrawing group. So that is how, if you do the Birch reduction on any salt, you get selectively this alpha beta 1,4 cyclohexadiene derivative. On the other hand, if we have an electron withdrawing group, for example, say for example we have ethyl benzoate. So in this case, the radical addition or the electron addition can happen at the para position, which can make sure that the negative charge will sit on the carbon attached to the electron withdrawing group. Okay. And this one is very stable because the electron withdrawing nature of this group will stabilize this negative charge, but the electron releasing group will normally destabilize it. So if we have a benzoic acid or a derivative of benzoic acid, the Birch reaction or the Birch reduction reaction usually results in the formation of a compound such as this. So the position of the double bond. So if you look at the electron releasing group, the electron releasing group product will be having the double bond in conjugation. But in the case of electron withdrawing group, the double bonds will be away from this carbon atom. So that means two double bonds will be in the vertical position. So remember, these are the regio selectivity issues in a Birch reaction. And so this is, as I told you, something very, very frequently asked question. So if we have anisole, add lithium in ammonia and ethanol, what will be the product? Or it can be also a xylene derivative. So if you have orthoxylene, you treat it with sodium and ammonia, and what will be the product? So it will lead to the formation of a product where these two will be in the double bond sits in between the two groups because of the electron releasing nature of the functional group. And also, as an application, say for example, if you have this orthomethoxy benzoic acid, what is the best method to convert this into an alpha beta unsaturated ketone, a cyclohexenone derivative? What will be the reagent to be used? So this is one of the important application of the Birch reaction. So what happens is, so we know that if we have a benzene ring with a electron releasing group, the double bond will be in a conjugation. And if you have an electron withdrawing group, the double bond will be in the vertical position. So if you have these two combination, you have both the groups, then the product of a Birch reaction will be this is the product formed, the 1,4-cyclohexadiene, where if you consider the OMe group, the double bond is in conjugation, or double bond is attached to the carbon bearing the electron releasing group, and for electron withdrawing group, the double bond is away, which is not in conjugation. So everything is fine. And now this is an enol ether species which can easily be hydrolyzed under mild acidic condition to form the corresponding enol form, which can easily tautomerize to the keto form. So this can easily be converted into carboxylic acid, and this hydrolyzed to the enol form, and the enol form can easily be tautomerized to the ketone. And if we heat this reaction mixture, it can undergo a decarboxylation to form the the alpha beta unsaturated ketone system. So in one step, in a one pot reaction, so the Birch reduction and hydrolysis can combine to convert a benzoic acid derivative to a ketone derivative. So in addition to that, you can also use an alkylation strategy. So if you use an alkylating agent along with the Birch condition, we can easily alkylate at the carbonyl, the carboxylic acid position to introduce the alkyl group. So we'll see the mechanism of this reaction. So this is how this reaction works. So if we have a tertiary butyl ester or any carboxylic acid derivative, we know that the final product formed will be the acid where the double bond will be in vertical position. It is away from the carbon bearing the electron withdrawing group. And once the Birch reaction happens, what can happen is that the negative charge will be sitting alpha to the electron withdrawing group, which will be more stabilized. And once this anion is generated in the presence of an alkylating agent, this anion can easily get alkylated. So instead of protonation, which is happening normally in a Birch reaction, but if you have an alkylating agent like an alkyl bromide or an alkyl iodide, the anion can undergo a nucleophilic addition to this bromide, displacing the bromide to form an alkylated species. So this is also possible in some cases in Birch type reaction. So in the context of this dissolving metal reduction, there are a few named reactions which are somewhat very interesting. So one reaction, named reaction, is a Bowlett-Blank reaction, which is now commonly known as the Blank reduction reaction. So the reaction essentially is the conversion of a carboxylic ester into two molecules of an alcohol. So essentially, it cleaves the ester in presence of sodium and ethanol to form two molecules of alcohol. So what happens here is, if you have an ester moiety in the presence of sodium, so what can happen? Sodium, and at low temperature, this can donate an electron, and that electron that donated can add to the carbonyl to form a radical anion, just like what we have seen in the previous reaction, the Birch reaction. The radical anion in presence of ethanol, the anion gets protonated to form a free radical, and this radical can attract another electron from a second molecule of sodium to generate an anionic species, and this can again be protonated and to form an acetal form, and this acetal form can cleave the carbon-carbon bond to form the aldehyde, and to the aldehyde again the same process can proceed. So at this stage, the R2OH is generated and leading to the formation of the aldehyde, and this aldehyde can again reduce to a primary alcohol. So basically, you cleave the carbon-oxygen bond of an ester using sodium ethanol reduction condition. And in the same context, there is another reaction. Suppose we don't use, so here in the Blank reaction, one has to use sodium and ethanol. The ethanol or any protic solvent is responsible for the protonation of the anion thus generated to form a hydrogen oxygen bond in this specific case. Suppose we take only sodium, only metallic sodium without a proton source, what can happen is the electron can add to the ester, generating the radical anion, just like in the previous case. Now, this anion cannot be protonated because we don't have any ethanol solvent or a protic solvent. So instead, what can happen is that two molecules of this radical anion can combine together to form a new carbon-carbon bond to generate this intermediate, and this can eliminate two molecules of methanol to form 1,2-dicarbonyl compound. And to the 1,2-dicarbonyl compound, again, the same process can repeat. And in the end, this leads to the formation of acyloin reaction. So the acyloin condensation reaction starts from the ester to the alpha hydroxy ketone derivative. So this is the cyclic analog of the acyloin reaction. And one more reaction we discuss is the Wolff-Kishner reduction reaction. So I'm sure this is well known to you. So conversion of a ketone to a hydrocarbon, the complete reduction of a ketone in the presence of hydrazine and a base, which proceeds via the simple mechanism of a base-induced elimination of a nitrogen gas to form the conversion of a CO to CH2 moiety under basic condition using hydrazine is known as the Wolff-Kishner reduction. Okay, so with this, we complete our discussion on reduction reactions, and now we will move to the oxidation reactions in organic chemistry. So we have discussed, just like we saw yesterday, that the reduction reactions and oxidation reactions are one of the most important reactions in synthetic organic chemistry. And the reduction reactions are even more important because it converts a sp2-centered molecule to an sp3-centered molecule, thereby making a planar compound to a tetrahedral molecule, where you always have the possibility of creating a chiral center. And the oxidation is the just the opposite of this reaction. So it is, for inorganic chemist, it is a loss of electron or increase in oxidation number. I hope you will be remembering the oxidation of magnesium to magnesium 2 magnesium 2 plus yesterday we discussed. So in organic chemistry, again, we cannot see this oxidation process which does not include or involve a direct or a visible electron transfer, and hence we always call in organic chemistry context, oxidation is the addition of oxygen or the elimination of hydrogen. So oxidation reaction is otherwise known as the addition of oxygen. So if you take an inert hydrocarbon, such as this is a hypothetical case, you take ethane, you add a molecule of oxygen, or addition of water to ethylene, you can convert it into an alcohol, further oxidize to aldehyde or to corresponding carboxylic acid. So the oxidation can be an addition of oxygen, or in other words, this can have, we also defined as the elimination of or removal of hydrogen. So if you take ethane, you remove 2 hydrogen to form ethylene, or again 2 hydrogen to form acetylene. These are all the oxidation reactions. So oxidation in general is either the addition of oxygen or removal of hydrogen. And these are the some of the type of oxidation reactions. So this can happen at a single carbon. We can also be possible, it will be clear as we move along. If you have a functional group and the functional group will not be touched, the alpha carbon atom or a vicinal carbon atom will be oxidized, a heteroatom can be oxidized, and also an unfunctionalized, suppose you have a CH hydrogen which is inert, which can also be oxidized. So generally for oxidation reactions, we depend or we use different types of oxidation reactions. So the metal-based oxidation reaction, the metal containing oxidation reactions. The second is metal free oxidation reaction. So if you look at the metal based oxidation reaction, there are several metals useful for oxidation chemistry, and among the most important is the chromium-based oxidation reactions, and you also probably have seen the oxidation using manganese KMnO4 or manganese dioxide used for allylic oxidation reaction, then osmium, ruthenium-based oxidation, lead-based oxidation, lead acetate, or titanium-based oxidation. So we will be limiting ourselves to the chromium-based oxidation reaction, which is most important in the context of oxidation reactions. So almost all chromium-based oxidation reactions, say for example, the chromium trioxide, dichromate, or chromate, these all reactions start from the chromium 3 oxide. So chromium trioxide. So this is a starting point for all the oxidation reactions involving chromium. So chromium oxide, and there are different types of chromium-based oxidation reactions. So one is called Jones oxidation. The second is the pyridinium chlorochromate, pyridinium dichromate, Collins reagent, and rare cases chromyl chloride people use. And this reaction and the reactivity and the selectivity depends upon the reagent employed and also the condition employed. So in general, this is an oxidation reaction. So the chromium is in the 6 oxidation state. So the chromium 6 will be reduced under the reaction conditions, thereby oxidizing the organic compounds. So generally, if you take chromium 3 oxide, so chromium oxide, so Cr triple bond or 3 times oxygen, and if you have addition of water to chromium 3 oxide, so this can easily add to chromium to polarize one of the chromium oxygen bond to form a chromate. So the HCrO4 minus, and if we have a cation, say potassium, so it is like a potassium chromate, and 2 of this chromate, 2 of this like this, and this chromate can add to a second molecule of chromium trioxide to form a dichromate species. And the dichromate, again, if we have the potassium cation, we say it as K2Cr2O7 or potassium dichromate. So this, the oxidation of all functional groups with chromium, it all starts with this chromium trioxide. And if we add acetic acid instead of water, so if you add water to chromium trioxide, we get either a chromate or a dichromate, as we demonstrated here. And if we have a addition of acetic acid, same like the addition of acid to the chromium trioxide can take place like this. And again, a second molecule of chromium, the carboxylic acid can add to form an anhydride species. And this is not very important, but please remember this chromate and dichromate species generated under the reaction conditions. So if you take chromium trioxide, instead of water, just a nucleophilic addition of water, what we mentioned to generate the chromate or dichromate, if you use pyridine as a nucleophile, what will happen? The pyridine can add as a nucleophile and polarizing one of the chromium oxygen bond, which results in the formation of a citryonic species having a chromium nitrogen bond. And the most common transformation affected by this reaction, so all this chromium-based reagent, chromium 6 reagent, is the oxidation of primary alcohol to an aldehyde or a secondary alcohol to the corresponding ketone. So what essentially happens is you have an alcohol, you have a ketone, the chromium trioxide, So the lone pair of electrons adds to one of this chromium trioxide, generating this intermediate. This O- will be subsequently protonated. And with the assistance of the proton attached to this OH group, this can eliminate a chromium residue to convert this into aldehyde. And now the chromium has been reduced to the lower oxidation state from chromium 6. So that is how the reaction works. So the oxidation of secondary alcohol, or the primary or secondary alcohol, to an aldehyde or a ketone at the expense of the chromium oxidant, which gets itself reduced under the process. So there are different types of chromium reagents. So normal chromium oxide reagent, what we use is not very selective, because what happens in this reaction is we start with an alcohol which gets oxidized to the aldehyde or a ketone. So once you get the aldehyde or a ketone, the carbonyl compound is much reactive than the starting alcohol substrate. So this alcohol is always prone for further oxidation to form the carboxylic acid. So there are some reagents which has having some sort of selectivity, where you can stop the reaction at the intermediate stage. Say, for example, if you have a universal oxidizing agent people use is a Jones reagent. The Jones reagent is an aqueous acidic solution of chromium trioxide. So the chromium trioxide in aqueous acidic solution. So the chromium trioxide, what we have seen, the same chromium trioxide, the chromate in an acidic solution is known as the Jones reagent. And this Jones reagent is useful for the oxidation of all sort of secondary alcohol or primary alcohol to the corresponding aldehyde or the ketones. So the advantage of this chromium-based oxidation, the Jones oxidation, is, so normally the oxidant is a chromium 6-based oxidation, so the chromium trioxide, it gets converted into chromium 4, which is precipitated under the reaction condition. So one advantage of using Jones oxidation is that at the end of the reaction, the chromium 4 gets precipitated, so you can just decant the reaction mixture in, when you do the reaction in acetone as a solvent. So there is easy to do the reaction. But the disadvantage of the process is that this, even the Jones reagent also, the disadvantage of the Jones reagent is it is good for converting aldehyde to alcohol to acid, but we know that Jones reagent is the combination of chromium trioxide, acid, and water. So an aqueous acidic solution of chromium trioxide. The acid can be either HCl also. So what can happen is, in the first step, the alcohol getting converted into the aldehyde. In the presence of an acid and water, the acid can coordinate with the aldehyde, making it more reactive, and the water can undergo a nucleophilic attack on the aldehyde, forming the acetal derivative. And this acetal can be easily oxidized. One of the OH group can easily be oxidized to the corresponding ketone. In the end, the alcohol is completely oxidized to the corresponding carboxylic acid. So the second disadvantage of the method is the over-oxidation of the carbonyl compound to the carboxylic acid. And the third disadvantage of the Jones oxidation is, suppose we have the chromium trioxide in aqueous acidic solution, and if we want to do a oxidation of a substrate like this, an epoxy alcohol, and we use the Jones reagent. So our idea is to convert the epoxy alcohol to the epoxy aldehyde by oxidizing the primary alcohol to the aldehyde. But since the Jones reagent contains acid, it's an acidic solution of chromium trioxide, this acid sensitive functional group such as an epoxide will not be tolerated. So the epoxide will open up under the reaction conditions. How? The epoxide will be coordinated with the acid, and then you have water, so water can open up the epoxide. So in addition to the expected aldehyde, epoxy aldehyde, you also see the epoxide opening when you do this epoxy aldehyde alcohol oxidation using Jones reagent, because Jones reagent is an acidic reagent which cannot tolerate acid sensitive reagent. So what are the disadvantages of Jones oxidation? The method is good for converting alcohol to aldehyde, but in majority of the cases, the reaction does not stop at the aldehyde. It will be further oxidized to carboxylic acid. And the method is not suitable for acid sensitive functional group. And the second one, the third method is if you have some groups such as hydroxy functionality in the molecule under acidic condition, you can also think about the dehydration reaction to install a carbon-carbon double bond in the molecule. So there are some disadvantages of being using this Jones oxidation. So one
Excuse me, sir.
Yes.
So can we use any catalytic poisons to stop the oxidation till aldehyde only?
Sorry?
So you said that Jones reagent converts alcohol directly to carboxylic acid, right?
Yeah.
It is considered as a disadvantage also.
Yeah.
So can we use any catalytic poisons in order to stop it at aldehydes?
So there is no way we can use any poison this is not a catalyst. So we need this as a reagent. It is to be used as a stoichiometric reagent, because each of the chromium, you start with chromium trioxide, chromium at the 6 oxidation state, and when the alcohol is oxidized to the aldehyde, chromium is getting reduced to chromium 4. Okay, so it is not at all a catalyst. So you need to have the reagent in stoichiometric amount. This is what we have started discussing in yesterday onwards. For all reagents for oxidation reaction and reduction reaction, we need the reagent in stoichiometric amount. Some cases, say for example, sodium borohydride, ideally you need 1/4 of the reagent, because we have 4 BH bonds. Okay, so in this case, each chromium 6 will be reduced to chromium 4. So we have to use this stoichiometric amount. The issue here is, since this Jones reagent contains CrO3, acid, H2SO4 or HCl plus water. So this is the combination of this chromic acid or the Jones reagent. So what can happen is, when the aldehyde is converted to the, alcohol is converted to the aldehyde, even if you use one equivalent of the reagent, once this aldehyde is formed, the aldehyde itself is reactive, but in the presence of acid, it can be further activated via the Bronsted acid activation. And then the addition of water, which is also present in the reagent, to the aldehyde lead to the formation of this acetal. And to the acetal, a second oxidation can take place to form the, so simple like an alcohol converting to the ketone, an acetal can oxidize to form the carboxylic acid. So there is no way you can prevent the over-oxidation reaction. Okay?
Okay, sir. Thank you.
All right. So one thing I told you, or one of the disadvantage of Jones oxidation is that we cannot use an acid sensitive functional group. because if you use an acid sensitive functional group such as an epoxide or an alcohol which can undergo dehydration reaction under the oxidation condition. So this one disadvantage we can solve by using a different reagent. So instead of an acidic solution of chromium trioxide, we use chromium trioxide and add pyridine to that. So what will happen? So if we have chromium trioxide, pyridine, and if you add this can form a species like this, a sweeter ionic intermediate, and you can also think about a second molecule of pyridine addition, making one of the chromium oxygen double bond intact so that the nucleophile or hydroxy functionality can add. So here what is the advantage is you use only pyridine along with chromium trioxide, no water, no sulfuric acid, so it is anhydrous. So the advantage is that you can use this reagent for the oxidation of an epoxy system. Say for example, if you use the chromium trioxide pyridine for the oxidation of this epoxy alcohol, it reacts very well without affecting the epoxide functionality, or which does not affect this olefin, this oxidation will happen which does not undergo any isomerization of the double bond, which can possibly happen under acidic condition. So the advantage is the chromium pyridine, so this is Collins reagent, but then the disadvantage of this method is this salt formed is very much hygroscopic in nature, so it absorbs moisture from the atmosphere. So one has to handle this Collins reagent under inert atmosphere, and that is one reason it easily decomposes, and hence one has to use large amount of the reagent for doing a given transformation. So there is one advantage, so you can use acid sensitive functional group, but the disadvantage is that it is moisture sensitive and one has to use large amount of the reagent. So we saw the chromium based reagent, so the Jones reagent, so that is very good, which is useful for the reaction or the oxidation of alcohol to the aldehyde and ketone. But it suffers from some issues because of the presence of acidic moiety, so the acidic condition, so acid sensitive functional groups cannot be used. And one advantage for doing this is a use of Collins reagent, so the combination of chromium trioxide and pyridine, which is good to a certain extent, but that also suffers from some difficulties. So the most important application of this chromium based oxidizing agent is the pyridinium chlorochromate, which is otherwise known as the PCC. So the PCC is one of the best chromium based reagent for the oxidation reactions. So what happens is the chromium trioxide, so you always start from chromium 3, which generate the O minus, and this gets protonated to form this intermediate. And this intermediate, once you generate this hydrochlorochromate intermediate, and if you add pyridine to this reagent, what will happen is that pyridine is also a very good base, so the pyridine can abstract this hydrogen. So if it abstract that hydrogen, what will happen? So pyridine will convert into the pyridinium salt, N positive, so pyridinium salt, and the remaining anion will be generated. So that is how it is known as pyridinium chlorochromate, which is an orange yellow solid, which is crystalline and hygroscopic. And remember, this reagent is formed from chromium trioxide upon treatment with acid, followed by base treatment. So there is no acid, no base. It is just a salt, a crystalline salt formed from chromium trioxide, HCl, and pyridine. So this is a reagent which is used in stoichiometric amount with substrate, which is less hygroscopic, so it can be stored in bottle form in air. There is no problem, and it is very mildly acidic, because if we prepare pyridinium chlorochromate in the lab, it may contain traces of this HCl impurity, which can be neutralized by using sodium acetate as a base. So it contains, it is an acid or a base-free reagent, useful for all type of reduction reactions. So PCC can be used for the reduction or the oxidation of this primary alcohol to this aldehyde. So an acetal moiety, which will be unaffected, because normally under acidic condition, the acetal moiety will be cleaved. So nothing will happen. So all sort of primary and secondary alcohol, we can convert it into the carbonyl compound using the chromium-based oxidizing agent, which is PCC. So if we look at a simple olefin, it can be converted into a ketone along with the combination of PCC and a borane reagent. So we have seen yesterday hydroboration reaction and oxidation reaction, right? So if you have an olefin and add to hydroboration condition and oxidation reaction, what will happen is you get it converted into the alcohol, and this alcohol can be easily oxidized in the presence of PCC at 0 degrees Celsius to convert it into a ketone. So a two-step conversion of an unactivated olefin to a ketone can be accomplished by combining combining the borane reduction or borane hydroboration reaction followed by oxidation chemistry. So having said all this, one of the most important application of PCC or pyridinium chlorochromate in all the reactions, in all the oxidation reaction, is its remarkable ability to oxidize the allylic alcohol moiety. So if you have a allyl alcohol like this, in the presence of PCC and dichloromethane under dry conditions, what can happen is that one can easily oxidize this allyl alcohol to an alpha beta unsaturated carbonyl compound. So what happened essentially is you have chromium O minus, pyridine plus. So this is the reagent, so the PCC reagent, pyridinium chlorochromate. So if we consider the addition of this allyl alcohol oxygen to chromium, so this will polarize and eliminate this chloride, and this will result in the formation of this particular intermediate. And this intermediate now can undergo a 3,3 sigmatropic rearrangement. Say, for example, you are cleaving this carbon-oxygen bond, 1, 2, 3, 1, 2, chromium 3, oxygen 3, chromium is 2, oxygen is 3. So a 3,3 sigmatropic rearrangement cleaving the carbon-oxygen bond will make this intermediate. Under workup, this can easily oxidize to the corresponding ketone. So this is one of the most important application of the PCC in organic transformation. So it can oxidize an allyl alcohol to the corresponding alpha beta unsaturated ketone. So it is also possible that instead of an allyl alcohol, so suppose we have this substrate. Assume that we have this substrate. So in this case, earlier in the case of this allyl, this CC bond will cleave. So here the same rearrangement will proceed, cleaving this CC bond, and you get, in presence of PCC, you get a 7-membered ring compound with ketone. Sorry. Yeah, so it is there already. So if we have this type of compound, so instead of, as I told you here, the allylic system will cleave, a 3,3 sigma-tropic rearrangement will take place. So in this particular case, what will happen is this double bond will, this cyclopropane carbon-carbon single bond will cleave to form this 7-membered ketone as a product. So this is something very frequently asked for all sort of competitive exams after masters. So how you do this transformation, a ring expansion reaction, which is applicable by PCC. So again, coming back to the some of the functional group transformations. So if you look at this ketone substrate, so as I told you, PCC is useful for the oxidation of an allyl alcohol under the reaction conditions. So there can be the PCC reaction combined with various other transformation. So assume that if you do not have the allyl alcohol, we can generate the allyl alcohol from an alpha beta unsaturated ketone. Say for example, if you have a methyl grignard, so it will add to this ketone in a 1,2 fashion, 1,2 addition. So you generate the allyl alcohol in situ in its first step, and then a PCC mediated oxidation will lead to the formation of this product. And this is another wonderful example. So you have this alpha beta unsaturated ketone with a stereo center, and when you add methyl grignard, the grignard will add and you generate the allyl alcohol, then it will rearrange via the 3,3 sigma-tropic rearrangement oxidation cascade, and you get the product after a rotation. So you have essentially the product will be formed with a different stereochemistry because you have inverted the positions of these two carbons at the end of the reaction, because originally the methyl group is coming here, but in the product it is coming at this carbon as a result of the mirror image form structure. So this is also a wonderful example where you can combine the PCC oxidation with an allyl alcohol bond forming reaction. So again, in some cases where the pyridinium chlorochromate reactions, the PCC oxidation of a tethered olefin can be combined with the in situ cyclization reaction. Say, for example, if you have an alcohol which is tethered to an olefin, or which is connected to an olefin using a carbon chain, the PCC can oxidize this alcohol to the aldehyde. And once the aldehyde is formed, it can undergo an ene-type reaction to form this alcohol derivative, and this alcohol can further oxidize to form the ketone. So it can be combined with various functional group transformations. So here also the same thing happens. So the oxidation followed by cyclization can lead to the formation of the value-added products. So as I told you, pyridinium chromate PCC is one of the best reagents. So it is not acid containing. So one can use acid sensitive functional group base sensitive functional group. So if we start from the Jones oxidation or Jones reagent, so if you see Jones reagent, the problem is it is a good reagent, but it is a solution of acid, aqueous solution. So we cannot tolerate acid sensitive functional group. So we think about Collins reagent, but Collins reagent is containing the pyridine. So the problem with this Collins reagent is it is not very hygroscopic in nature. One has to use excess amount, and the universally accepted chromium containing reagent is PCC, pyridinium chlorochromate. But the only one disadvantage of PCC, if we ask what is the disadvantage of pyridinium chlorochromate, is the removal of this chromium residue. So at the end of the reaction, we need to do a workup. So we have to mix it with an organic solvent and transfer all the valuable material to the organic solvent, leaving the chromium residue in the aqueous layer to separate the molecule. So separate the compound from the chromium residue. So one solution for this is the purification issues associated with PCC is to use Pyridinium Dichromate Pdc. The advantage of PDC is, so PDC is you take chromium trioxide, 2 molecules, it forms the dichromate, and then you add pyridine, 2 molecules of pyridine, so it will abstract these 2 protons and you get this salt. So this is PDC, again a crystalline solid. But the advantage of this material is it is water soluble. It is soluble in Dmso, DMF, and dimethyl acetamide. So the reagent is very much soluble. So the purification issues are not very much like in the case of PCC, because in PCC we have to be very careful with the reagent in eliminating the chromium residue. But in PDC, since the reagent is water soluble, at the end of the reaction, you add water to the reaction mixture. So all the unreacted pyridine residue or the PDC residue will dissolve and leaving behind your product in organic layer. So it is much easier to purify the reaction mixture at the end of the oxidation reaction using pyridinium dichromate, so PDC. Yeah, so this is again PDC can be useful. So in this PDC oxidation, so it can further oxidize the aldehyde alcohol to the aldehyde. So if we have excess of reagent under heating condition, this can undergo an Ene type reaction as we discussed earlier. So yeah, this is also one of the important application of PDC. So the PDCs and PCC, they are very selective, and you can convert the alcohol to the aldehyde without further oxidation. So there is another advantage because there is no acidic impurity present in the reagent. So it can either be PCC or PDC, but people prefer PDC over PCC because of its water soluble nature. So that makes it much easier. So to summarize, regarding the oxidation or reaction using chromium based reagents, so most of these reagents used the transformations primary alcohol to an aldehyde. One can use PCC, Collins reagent, PDC in DCM. So these reagents are very selective. And for the secondary alcohol to ketone, we can use PCC, PDC, Jones reagent also, because the ketone cannot be further oxidized. And if you use the alcohol, if we use PDC in DMF, the DMF solvent is always associated with traces of moisture, which will do the further oxidative cleavage or oxidation of the aldehyde generated to convert it into the over-oxidized carboxylic acid product. So normally people use PDC or PCC, so PCC in dichloromethane as the solvent. So in dichloromethane, this is an anhydrous condition, so there is no moisture involved, so the reaction will be very selective. So that's all about the manganese containing, the chromium containing oxidation reactions. So we have seen the Jones oxidation, the merits, the disadvantages, Collins reagent, then PCC, and also the PDC reagent. And we have seen what are the most important reagent is most likely PDC, the Pyridinium Dichromate, which can be used and very easy to remove because it is a water soluble reagent. So at the end of the reaction, you can add water to the reaction mixture so that all the chromium reagents, the unreacted PCC and all the chromium residue will dissolve, so that easy to separate the organic compound from the inorganic residue. So now we will move to the manganese containing oxidizing agent. So I will not spend much time on this manganese oxidation reaction because these are all known to you. I'm sure KMnO4 can do a cis hydroxylation reaction, so leading to the formation of a cis diol, and the cis diol again can probably under the reaction condition gets oxidized to the dicarbonyl compound, and this is something very known. And these reactions, the KMnO4 reactions and manganese dioxide reactions are also known to you. I'm sure this is all known to all of you, how to use KMnO4 or manganese dioxide based oxidation reactions. So now we'll move to the metal-free oxidation reactions. So the reactions, the oxidation reactions without the use of metals, or metal-free oxidation reactions. So one of the important aspects, or one of the important reaction in this domain, the oxidation using metal-free condition, is the oxidation reaction using dimethyl sulfoxide. The dimethyl sulfoxide, or otherwise known as Dmso. This is one of the important reagents useful for the metal-free oxidation reactions. Metal-free oxidation reactions. So the idea is the combination of dimethyl sulfoxide with various electrophile can be classified into several named reactions. Say, for example, if you use Dmso with oxalyl chloride and triethylamine, the combination is known as Swern oxidation. The other reactions are Fisner-Moffat oxidation, Kornblum oxidation, Korekim oxidation, and the combination of Dmso acetic anhydride. So we will see all these reactions. First, we will see the Swern type oxidation reaction. So what is Swern oxidation? So again, these are all oxidation reactions where you convert an alcohol to an aldehyde. And the challenge will be how to stop at the aldehyde, because in most of the oxidation reactions, so even we say PCC is very selective, but sometimes the PCC oxidation can also lead to little bit of over oxidation of this aldehyde to carboxylic acid. But these metal-free oxidation reactions are very, very selective. It will simply stop at the aldehyde. It will not proceed mechanistically the further oxidation reaction. So let's see what will happen, what is happening in a Swern type oxidation reaction. So Dmso, dimethyl sulfoxide. So this is a nucleophilic reagent, so the O minus, so it can also be written as, this is what people normally write, dimethyl sulfoxide, or the sulfur oxygen bond is polarized towards oxygen, so in citrionic representation. So if we add Dmso to oxalyl chloride, the negative charge, the nucleophilic species, can add to the carbonyl, eliminating the chloride. So a chloride is eliminated, and now the eliminated chloride can come back and add to the thiazolium species thus generated, which will eliminate a molecule of carbon dioxide and a carbon monoxide and a further chloride to form this intermediate. So a dimethyl sulfonium chloride. And this is the key intermediate in Swern oxidation, the key electrophilic intermediate in Swern oxidation reaction. And when we so it can add to the sulfonium salt to release a chloride minus chloride to form this species. And in the end, we also use triethylamine in excess. The base will abstract a proton from the carbon atom attached to the alcohol to eliminate the dimethyl sulfide to form the product. So in the end, in a Swern oxidation reaction, if you convert an alcohol to a ketone, a secondary alcohol to a ketone, dimethyl sulfide, carbon dioxide, carbon monoxide, and the chloride eliminated will add to the triethylamine base to form the triethylamine hydrochloride. So these are the side products of the Swern oxidation reaction. So the Swern oxidation reaction is really useful because most of these reaction products, so like dimethyl sulfide, carbon monoxide, and carbon dioxide, these are gases. Obviously, dimethyl sulfide is not a very good gas. It is a foul-smelling gas. But nevertheless, the reaction is driven by thermodynamics, because whatever gas formed will evolve from the reaction mixture, making the reaction always in the forward direction. So remember, in the case of Swern oxidation, the reaction is dimethyl sulfoxide addition to oxalyl chloride in the presence of triethylamine, and this leads to the formation of the product, the oxidized product. The aldehyde is the alcohol is oxidized to the aldehyde under the reaction conditions. All right, so whenever we do the Swern type oxidation reaction, these Swern oxidation reactions are always carried out at a very low temperature of minus 78 degrees Celsius, because the reaction should proceed at a very low temperature. Otherwise, at room temperature, if you perform the room reaction at room temperature, what can happen is, say for example, this is a key intermediate formed as a result of the addition of the aldehyde, or sorry, the alcohol to the electrophilic sulfonium salt reagent. So at room temperature, this sulfonium salt can deprotonate, the CH proton can be eliminated, and this can add to the oxygen, breaking the sulfur oxygen bond to form a disulfide. For thioacetal moiety can be generated. Thioacetal moiety can be generated. There is a possibility for the formation of an halide and a thioacetal at room temperature. So always one has to do the Swern oxidation reaction at low temperature if possible. So if you look at this substrate, we have a secondary alcohol moiety, we have an acetal, again an acetal, and a carbon-carbon double bond. So all these functionalities will be untouched under the Swern oxidation condition, and only the alcohol will be converted to the ketone without affecting the functional groups, the acetals or any other functional groups. So this reaction is highly robust, and also this does not create any issue with for the stereospecific oxidation reactions. Say for example, if you have this homoallylic alcohol, the Swern oxidation could result in the formation of this aldehyde, where the hydrogen atom cannot epimerize under the reaction conditions. So because we use only a mild base in Swan oxidation reaction.
Dr. Biju, I have a question.
Yes.
Do you really require that minus 78 degree temperatures? I mean, what is your practical experience? Have you ever done this reaction in the laboratory? Because I just wanted to know whether freezing
so
mixture will work.
I have done Swan reaction during my PhD time and also during my postdoc time. So the Swan oxidation, you don't have to do at minus 78 degrees Celsius, but the problem is it is recommended to do at a very low temperature, because at any temperature above 0 degrees Celsius, we have the problem of the ylide generation, and the ylide will convert into a thioacetal without the oxidation of our expected primary alcohol to the aldehyde or a ketone. So this is always a side product in Swan.
My question was just wanted to know whether is it possible using a ice salt freezing mixture will do, or we need really that cooling device, liquid nitrogen.
Ice salt freezing mixture can go only up to minus 10 degrees Celsius. It will not go beyond that. So in most of the cases, people use at least minus 40 degrees Celsius, one can use in acetonitrile bath using liquid nitrogen to reduce the temperature to minus 40 degrees Celsius. So normally people do it at minus 40 degrees Celsius to minus 78 degrees Celsius, which will make sure that the reaction is complete without any side product formed in this Swan type reaction.
Okay, thank you.
All right, so that is Swan oxidation. So the Swan oxidation is, as I told you, it is a metal-free oxidation reaction, which is widely used for.
Sir, previous slide.
Sorry.
Previous slide, sir. One show me previously. Previous. First one of the Swan oxidations. Previous.
Yes. Here.
Sir, here chlorination. How does it happen, sir?
Sorry.
Chlorination here. Last example, sir. In that chlorination, how does it happen?
Okay. So this is probably a mistake. This chlorine is this is here. It is hydrogen. Okay. So in some cases, what can happen is under basic condition. So if you have this reaction happening, the Swan oxidation of this alcohol to this ketone, and if we have excess of base, there is a possibility that the base can abstract the CH proton, okay, to convert it into an enolate, and this enolate can add to this enolate can add to the chloride. So there is a remote possibility. So this is sometimes it can happen if we use excess of the reagent, because there will be always chloride anion in the reaction medium that can alpha chlorinate under the reaction condition in rare cases. Okay.
Yes.
Okay, so good. So the next is we will see some of the variants, so some of the different examples or variants of the Swan oxidation or the Swan type oxidation reactions. Essentially, the oxidation reactions using Dmso. So one is the Fissner-Moffat oxidation reaction. Fissner-Moffat oxidation. So these are if we learn Swan oxidation, all other oxidation reactions are relatively easy. We'll just change one of the reagent, and the remaining things are all same. And also the intermediate reagents are also same in all the reactions. So in Fissner-Moffat, what happens is that we take Dmso and a carbodiamide like DCC, where R is equal to cyclohexyl, dicyclohexyl carbodiamide, and again the Dmso oxygen can undergo a nucleophilic addition, and the anion generated can be protonated, and this can again lead to the formation of this intermediate species, and the anion can add to the sulfur and getting converted into the product and dimethyl sulfide along with the dicyclohexyl urea. So the dicyclohexyl urea will be the side product. So here the dicyclohexyl urea will be the side product of the reaction. So that is what one can consider that as a disadvantage of the process, because in the typical Swan reaction, you don't have any side product like this, because all are mostly gases like carbon dioxide, carbon monoxide, and dimethyl sulfide. But in the Moffat oxidation, when we use DCC, dicyclohexacarbodiamide, the carbodiamide is getting converted into the urea derivative. One has to think about how to remove that urea derivative under the reaction condition. But the Fischer-Moffat has an advantage. So if we use the Dmso and DCC combination and triethylamine, so a base finally used to abstract the proton. And this is useful for some of the oxidation reactions containing sensitive functionalities, such as this functional group can easily undergo cleavage under acidic conditions. So if you look at Swan oxidation, one has to use oxalyl chloride. So the oxalyl chloride, even if you try to prevent, it will contain traces of HCl in that. So that HCl can create some issues to some functional groups. So some cases, the Fischer-Moffat oxidation reaction will be having some advantage over the classical Swan type oxidation. Also, in a different context, one can also use acetic anhydride. So acetic anhydride as the electrophilic species instead of oxalyl chloride or the carbodiamide used in Fischer-Moffat reaction. So what will happen is the sulfur Dmso will add to the acetic anhydride, forming an acetate anion, and this intermediate will be generated. And as earlier, this is only difference is the chlorine is replaced by the acetate. So this is also a good leaving group. The alcohol adds to the sulfur, generating the sulfonium salt, and the same acetate can come back and deprotonate, leading to the formation of the product. So this leads to the formation of acetic acid, not acetic anhydride. So this forms acetic acid as the final product. So one advantage people say in this acetic anhydride reaction is the alcohol generated. The alcohol can directly add to the acetate to form some side product. And instead of the acetic anhydride, one can also use the sulfur trioxide pyridine method. So if you have sulfur trioxide and pyridine, so this lone pair of electrons on pyridine can add to sulfur trioxide, generating this trionic species. And to this Dmso, if we mix Dmso with that, that can add to the oxygen can add to the sulfur, eliminating the pyridinium species. You get this reagent, and again the alcohol can add in this typical normal process to form the aldehyde and dimethyl sulfide. So just a variant of the Fischer-Moffat or acetic anhydride containing combination along with Dmso. So far we have seen the conversion of alcohol, the primary alcohol to aldehyde, or the secondary alcohol to ketone using the Swan type oxidation reaction. And in the Swan type oxidation reaction, the hydrogen attached to the alcohol containing carbon is very important. So we cannot apply, so we can apply this to a secondary alcohol but we cannot apply this strategy to a tertiary alcohol R2, R3, because this tertiary alcohol will not undergo Swan or any type of oxidation because of this absence of this CH proton, which is responsible for the final elimination. So what are the other options for doing a oxidation reaction instead of an alcohol? So one solution is, if you take, instead of an alcohol, an alkyl halide, just an alkyl halide, so a benzyl bromide derivative. And if you treat benzyl bromide with Dmso, what can happen is the Dmso can simply add to the benzyl bromide and eliminate the bromide to form this simple intermediate. And in the presence of base, this can directly convert into aldehyde and dimethyl sulfide as a side product. So this oxidation reaction is known as the famous Kornblum oxidation. So if you take benzyl bromide, this can be useful for converting benzyl bromide to benzaldehyde. So without using oxalyl chloride or any other reagent, or you don't have to proceed via the benzyl alcohol also. Directly a alkyl halide can be converted into a aldehyde derivative by using the Kornblum oxidation condition. And maybe the last method is, so far we have seen all reactions where we start in the metal-free oxidation strategies, or we always start with dimethyl sulfoxide. And dimethyl sulfoxide is a very good nucleophile. The oxygen will add as a nucleophilic species to an electrophilic species, generating the reactive intermediate electrophile. To that, the alcohol will add, and then subsequently the reaction proceeds. And most of this reaction, the fate of dimethyl sulfoxide is that it gets converted into dimethyl sulfide. So there is another oxidation reaction which uses dimethyl sulfide, the foul-smelling gas, the dimethyl sulfide as a reagent, dimethyl sulfide reagent for doing this oxidation reaction, which is another name reaction, which is called Corey-Kim reaction. So if you take dimethyl sulfide and N-chlorosuccinimide, NCS, so the dimethyl sulfide can undergo a nucleophilic addition from the sulfur, picking the chloride and then converting this into a succinimide intermediate, thus generating this intermediate. This is something similar to the intermediate in a typical Swan reaction. So a secondary alcohol can add, and following the same sequence of steps under basic condition, it can convert it into the secondary alcohol can be converted into a ketone, and we regenerate the dimethyl sulfide. So instead of dimethyl sulfoxide, the Corey-Kim oxidation utilizes dimethyl sulfide as a reagent for doing oxidation reactions. So far we have seen the oxidation reactions using dimethyl sulfoxide as the medium for oxidation reaction. But there are some other reagents which are also useful for doing oxidation reaction under metal-free conditions. One such reagent is the hypervalent iodine-containing reagent. So hypervalent iodine reagent, one is IBX, and the second one is DMP. So IBX is 2-iodoxy-benzoic acid, iodoxy-benzoic acid, and DMP is des-Martin per iodinane. Again, a hypervalent iodine reagent, so the iodine 5 reagent. So what people generally prepare this compound, the IBX, is using an orthoiodobenzoic acid in the presence of an oxidant such as oxone or potassium bromate. One can easily extend the oxidize this -1 iodine source to +5 oxidation state in the presence of an oxidant to prepare this intermediate IBX reagent. And once you have this intermediate, so the IBX as a very famous oxidant for doing oxidation of alcohols from primary or secondary alcohol to convert it into aldehyde or ketone. So what generally happens in these reactions is, so an alcohol, as usual, it is a nucleophilic species. That nucleophilic species adds to the hypervalent iodine containing species, and one of the alcohol moiety will be eliminated, and which leads to the formation of this species, and then again an elimination of this iodonium species. So will happen to form the aldehyde ketone product from a secondary alcohol, leading to the formation of iodine 3 reagent. So we started from iodine 5 and ended up with iodine 3. So this is one of the main application of benzoic acid, hydroxybenzoic acid, or IBX in doing oxidation reactions. So this can also oxidize the secondary alcohol to the ketone without affecting the enol ether moiety. So this is not at all an acidic reagent. So the enol ether moiety will be unaffected under the reaction condition. So Des-Martin periodinane is again, one can easily prepare from this hypervalent iodine reagent, the IBX. If we treat it with acetic anhydride, so acetic anhydride, so one of these oxygen can add to this acetic anhydride and eliminate one more acetate, and the eliminated acetate also can add to form the acetate containing reagent, which is nothing but the hypervalent iodine reagent. So the hypervalent iodine reagent, which is otherwise known as the Des-Martin periodinane, and the mode of addition is almost the same. So the alcohol will add to the iodine, eliminating one of the acetyl moiety, and then the hydrogen assisted elimination to get the iodine 5 to iodine 3. So iodine is getting reduced at the expense of the alcohol getting oxidized to the aldehyde. So the Des-Martin periodinane again have different types of oxidation reactions. So one of the important advantage of this Des-Martin periodinane containing oxidant is, if you look at this Des-Martin periodinane DMP oxidation, so you can see 3 acetate moiety. So if we have an alcohol having a secondary alcohol moiety and a primary alcohol moiety, we can have some sort of selectivity, a primary alcohol addition to this iodonium species than the secondary alcohol addition, because the primary alcohol is more exposed than a secondary alcohol. So one advantage of using the Des-Martin periodinane oxidant is selectivity for the primary alcohol over the secondary alcohol. So if you use exactly one equivalent of Des-Martin periodinane, one can get conversion of the primary alcohol to aldehyde. Even with excess amount also, the secondary alcohol moiety will not react so fast under the reaction condition unless we use a heating condition for doing this reaction. And another reagent that is not very important, so a reagent which is otherwise known as the TEMPO, the tetramethyl piperidine nitroxide, piperidine N-oxide. The reagent, again, it is useful for the oxidation reaction. So the oxidation reaction for, again, because of the presence of the sterically demanding moiety present, this reagent will be very good for oxidation of a primary alcohol, even in the presence of a secondary alcohol moiety. Good. So that brings me to the last topic of oxidation for today, the metal-free oxidation reactions. The last topic for discussion is the epoxidation reaction. So the epoxidation reaction is also one of the most well-known reaction for introducing a carbon-oxygen bond or converting a carbon-carbon double bond into carbon-oxygen double bond using mainly a per acid containing system. So before we go to the oxidation reactions or the epoxidation reactions, we should know the epoxidation reaction usually happen on a carbon-carbon double bond, and this gets oxidized to an epoxide. Depending upon the nature, the electronic nature of the olefin, we need to have different type of reagents. Say, for example, if you have this cyclohexene, 1-methyl cyclohexene, so this carbon-carbon double bond is electron neutral or electron rich substrate because of the presence of the methyl group. By virtue of the hyperconjugative effect, the carbon-carbon double bond will be relatively electron rich. But on the other hand, if we have an alpha beta unsaturated carbonyl like cyclohexene, hexenone, because of the presence of this carbon-oxygen double bond, this carbon-carbon double bond will be very much electron deficient. So here we have an electron rich system, here we have an electron deficient system. So depending upon the nature of the reagent, nature of the olefin, one has to use different types of epoxidation reagent. So generally what people do is the per acid based reagents are useful for epoxidation reaction, which can selectively transfer one of the oxygen of a per acid to the carbon-carbon double bond. Thereby, the per acid will be converted into a carboxylic acid, and the oxygen will be transferred to the olefin to form an epoxide. So generally, the reagents used are per acetic acid, per benzoic acid, MCPBA, oxone, dimethyl dioxidant, and usually the per acid one can easily prepare from the carboxylic acid upon treatment with a hydrogen peroxide, and we get the per acid moiety. And in the per acid, this OO bond is very weak, and that gives the enhanced reactivity of all per acids. So if we take an electron rich or electron neutral olefin, the reaction proceeds a typical butterfly type mechanism where a concerted process using the per acid moiety. So what happens here is, so you have an olefin and sorry. So we have the per acid like this. Oops, sorry. So per acid, I will write like okay. So the per acid can be drawn like this. So the olefin will add to this oxygen, the per acid oxygen, such a way that the electron richness of this carbon-carbon double bond can be utilized for the addition of this carbon-carbon double bond to the per acid oxygen, thereby cleaving this OO bond. As I told you, the oxygen-oxygen bond of per acid is really weak, and that is the key for all sort of epoxidation reactions. So this is a concerted process, and as I told you, this reaction is initiated by the olefin, and the electron richness of the olefin is the key to the success of olefination, this epoxidation reaction. So, in contrary to what we usually observe, if an olefin is tetra-substituted with 4-methyl group, so because of the hyperconjugative effect of the 4-methyl group, this carbon-carbon double bond will be highly electron rich, so that electron pair can be easily donated to the pair acid. So this a tetra-substituted olefin reacts faster than a tri-substituted or a mono-substituted olefin will react slower in epoxidation reaction. So the reactivity of the para acid is increased by electron withdrawing groups. So because the para acid, the electron withdrawing group is present, that will make it further electrophilic. So the typical para acid used in epoxidation reactions are metachloroperbenzoic acid. So metachloroperbenzoic acid, and this is something very important, which is frequently useful in all problems involving epoxidation reaction, because normally people feel like if you have 4-methyl groups, the sterics will prevent the epoxide oxygen approach, but it is not the sterics, but the electronics favors the epoxidation reaction. So if the olefin is tetra-substituted, say for example, if you have an olefin like this, a triene derivative, where you can see that this double bond is doubly substituted, this double bond is doubly substituted, but the middle double bond is tetra-substituted. So this middle double bond will be more electron rich. So the product formed will be from the middle double bond epoxidation. So the terminal oxygens are unaffected, and oops. So I can draw the product here. So this will be the product formed. According to the electronic nature of the olefin, the selective formation of the epoxidation will happen. And moreover, this reaction is a highly stereoselective. That means if you have a trans olefin as a substrate, we get a trans epoxide. And if you start with a cis olefin, it gives a cis epoxide as a major product. And this also, the reaction is governed by sterics to a certain extent. So for example, if you have a cyclopentene derivative like this, where these 2 hydrogen atoms are projecting below the plane, that means that the cyclopropane ring is projecting above the plane, so that cyclopropane can have some sort of effect on the epoxidation reaction. So selective oxygen approach for epoxidation takes place from the bottom phase to form the single diastereomer. So this is something important. The sterics of the cyclopropane will allow the epoxide formation from the bottom phase. And this is the example I just now showed you. If you have a multiple double bond in a molecule, the more substituted double bond will be easily undergoing epoxidation reaction, because that double bond will be more and more electron rich. And there is another combination of epoxidation reaction. So instead of the epoxidation using perbenzoic acid, one can also use the peroximidic acid, because this is always useful for epoxidation of acid sensitive substrate. Acid sensitive substrates, say, such as an acetal or other functionalities which will react with the acid functional group, because if you use MCPBA oxidation, the side product of MCPBA oxidation will be the 4-chlorobenzoic acid. The per acid will be converted to benzoic acid, and if this benzoic acid can create some issues to the acid sensitive functional group in the molecule, the choice for epoxidation reaction is, instead of the acid, you take nitrile and add hydrogen peroxide. You get peroximidic acid. It is not very reactive, that the per acid, and this peroximidic acid also can do the same job by transferring this oxygen to this olefin, converting the peroximidic acid to an amide. So earlier MCPBA will convert it into acid, but peroximidic acid will be converted into an amide. So acid sensitive functional groups can be tolerated under the reaction conditions. And in rare cases, one can also use carbodiamides along with hydrogen peroxide for epoxidation reactions by using this strategy. The so-called peroxide linkage, a sort of peroxide linkage is formed, and this can be transferred to the olefin to form the epoxide. So that is generally the method useful for the epoxidation of electron rich or electron neutral olefin. But on the other hand, if we have an electron deficient olefin like cyclohexenone, the reagent of choice is simply hydrogen peroxide under basic conditions. What will happen is, in the presence of NaOH, base abstract a proton generating the peroxyanion, and this peroxyanion can undergo a Michael type addition to the 1,4-diketone, and this enolate thus formed can come back and attack this oxygen, clear this oxygen bond to form the epoxide. So this methodology is useful only if the carbon-carbon double bond is electron deficient, because if the carbon-carbon double bond is electron rich, we cannot use this strategy because this it is not electrophilic enough. So we use the per acid as the electrophilic source and the carbon-carbon double bond as the electron rich substrate. So this is also the epoxidation reaction. In some cases, say for example, in the case of a methacrylate derivative, where if we want to epoxidize this carbon-carbon double bond using MCPBA, the reaction may not work because the generated carboxylic acid will cleave the ester back to acid. So the reagent of choice is an electron deficient carboxylic acid such as trifluoromethyl acetic acid derivative. This will be useful for methacrylate or ethyl cinnamate epoxidation reaction. And to summarize, if we have a functional group, or if we have a substrate which contains an isolated carbon-carbon double bond and an alpha-beta unsaturated carbon-carbon double bond. So this, please note, this is a very useful equation which is frequently asked in all competitive examination. Which reagent will be used to epoxidize this carbon-carbon double bond and isolated carbon-carbon double bond, and which reagent one can use for epoxidation of this alpha-beta unsaturated carbonyl compound. So if you use MCPBA, MCPBA is an electrophilic source of per acid. So the isolated carbon-carbon double bond will add and the epoxidation happens here. But in the case of hydrogen peroxide, it will add to the electron deficient carbon-carbon double bond to form this epoxide. So I hope that is all about Baeyer-Villiger oxidation. I think you have studied a little bit about it. So with this, I hope I was able to give you a take-home message on the oxidation reactions in the last 2 hours. If you have any questions on what we have discussed, feel free to ask. I will try my best to help you. Thank you.
Yeah. Students, it's your turn. If you have any questions, please feel free to interact with the resource person. I think some questions were asked during the session, but if you have any more questions, please.
Yeah, feel free.
Feel free to ask.
I will share the PDF of both the presentations today evening, so that in case you want to share to students, it will be useful. So, yeah.
So, Dr. Biju, I have a question, just one. When you are doing Dmso reaction, like Swan oxidation, What is the solvent? Is the Dmso, can we use it in bulk and can itself act as a solvent and add oxalyl chloride to it?
Yeah, we can use it as a solvent for the reaction. Yeah.
PCC we have used, but we usually do it on silica gel, right? We can also adsorb onto silica.
PCC.
Yeah, PDC and PCC, we'll adsorb it onto the silica, and we usually add the silica. We used to do that way because we can store it. That is a little bit easy instead of preparing it the right away. We'll add on to the silica gel.
PCC.
Yeah, PCC, pyridinium chlorochromate. Adsorb onto silica and use that silica. That was more convenient way of.
For PCC, not PDC, right?
No, not PDC, PCC.
Okay, yeah. PCC, it is fine. Yeah, the idea is it is much easier to remove the chromium residue.
Yeah, yes.
Yeah.
Students, if you have any questions, please come up. Any questions regarding how to face interview at IISc? So how do they go about from a very simple question to, I think here everything is here. They'll ask you to write a simple oxidizing agent, and then they'll ask on change the pH conditions, add more liable functional groups, and how you bring about. Maybe that is the kind of questions they ask you.
For our PhD interviews, we say these are some of the, whenever I am telling that this is frequently asked question in CSIR or GATE, these are the questions we ask students here. But surprisingly, many times the students say, if I ask a student giving cyclohexene, what is the reagent to use for epoxidation reaction, students will immediately write MCPBA. So I don't know whether when they come for the interview, they feel they are a little bit nervous or any things like that. But cyclohexene, they never write hydrogen peroxide in NaOH. They write MCPBA. So they don't have that idea about that which type of
electron-deficient and electron-rich double bond.
Yeah, which reagent will be useful for which olefin. And also if we write like two double bonds, which is a di-substituted and a tetra-substituted, and I want to specifically do the epoxidation of the tetra-substituted double bond, students will say, hey, it is very difficult to do it because of sterics. Because they always have that tendency to realize that whenever there is a bulky group, that whatever functionality or whatever functional group transformation you are doing, it will not work. But epoxidation is different.
That's true. Now, that was the specialty of this class. You always compared with the different functional groups. So students, those who have seriously attended this sessions would have benefited immensely, because you are always showing the two sides, one electron-rich bond, electron-deficient bond, different types of alcohols. So this is very easy to remember also, different reagents. Many times students ask, why do you need so many reagents? This is exactly the reason why you need so many reagents.
Yeah, so if we, instead of by-hearting it, if we compare, so like when we start with chromium-based reagents, start from John's reagent. So the difficulty with John's reagent is it is an acid solution of acid. So acid-sensitive functional groups cannot be tolerated. So we'll move to Collins reagent using pyridine. And there the problem is that it is very hygroscopic, but still you can perform the reaction using an acid-sensitive functional group. So if we want to oxidize an epoxy alcohol, the best reagent is Collins reagent, because the epoxide will not be affected. And then problem with these reagents are the aldehyde will be oxidized further to the acid. So there comes the application of PCC. And PCC is a universal reagent, and also the allyl alcohol rearrangement I showed. This, if you see, last 3 years CSIR or GATE, at least once this question will be there. Either the allyl alcohol or the allyl double bond will be substituted by the cyclopropane. This is a very frequently asked question. May not be the 6-membered fused, but similar question. Students will be asked to write the reagent or how this transformation takes place. So that PCC, PDC, one of the chromium-based reagent question is most likely it will happen in GATE or CSIR. And then the problem with PCC is it is difficult to remove the chromium residue at the end
Yes.
of the reaction. So then the alternative is PDC, so it is a water soluble reagent. So if we can combine all these things and start from the reagent and see how we can address the issue with a reagent and learn what is next. So it will be relatively easy for them to probably to learn. I don't know. When I was a student, it was very difficult for me also, to be honest.
Yeah, I remember.
Sir, I have
those
one
days.
question.
Yeah.
Yeah. Yes.
Sir, sometimes we use urea hydroperoxide for epoxidation. Is there any advantage for it?
Sorry, which one?
Urea hydroperoxide. H2O2 with urea.
H2O2 with urea. So that is what I showed you, the H2O2 with carbodiamide. That is or sometimes useful. Yeah. It's not urea, carbodiamide.
Okay, sir.
Yeah. So the idea is all these reactions, the weak nature of that oxygen-oxygen bond is key to the success of all sort of epoxidation reaction. But also we need to know which reagent, say like the nature, the electronic nature of the double bond is the most important thing. Whether the reagent is MCBVA type or a simple hydrogen peroxide under basic conditions. Yeah.
Students, any more questions? I think they will go through the slides and learn more about these reactions after they complete. Of course, MSc students, they are covering all these portions. So that will be much easy for them to understand.
Yeah, so I did not go very deep. So like the CBS catalyst, I was thinking that I will skip it because I felt like it is covered in a master's syllabus. But yeah, if we try to cover in 2 hours too many things, students feel like it is too much for them, right? But if we give a feel to them that it is too much, they probably don't learn even the simple things also.
Yeah, that is.
That's why I did not. I just screened that CBS yesterday. Also, we did not have enough time. But then, since you told that it is useful, then yeah, why not?
There are
Sir, I have one more question.
Yeah.
Sir, if we take styrene under the Birch condition,
Mm-hmm.
what will be product?
Styrene.
Yes, sir.
I think the cyclohexadiene, which will be in conjugation to the styrene double bond.
Sir, it is actually a previously asked question, I guess in GATE.
Yeah, this will be the major product. Because
Okay,
the
sir.
olefin moiety in styrene is not electron deficient.
Yes, sir.
Okay. So it can be considered as a, say, if you like take anisole OMe, like electron releasing nature, this could be considered as an electron donating substituent.
Okay, sir. Thank you.
Your double bond will be having the electron releasing group.
Yeah.
One of the double bonds.
Yeah, but if you have a ester or nitro group on that olefin, then things will be different. Because the double bond is electron neutral, right?
Yes.
Okay, sir. Thank you, sir.
Yeah.
So, if there are no more questions, we should officially thank you, Dr. Biju. It was a wonderful session, and you are really taken a lot of time. You know how busy you should be, and it was almost non-stop. Even I didn't see you taking water during the entire 2.5 hours of time. It's really, we know how difficult it is to take such a class. So thank you very much for your interest and interest to associate with us, and also to pass on
If the students are getting a take-home message at the end of the day, I'm very happy.
Yeah, that's what we also think. So that should be appreciated in front of them. The time you are taking, because you are not, the prime area is not teaching. Of course, you should be
That's why
research, how
I
much of
also
time.
told Jomon when in the one of the first email that it may be difficult to cover in 4 hours. So I sort of requested him, can I get 4 more hours so that we can. So like next week, what I'm planning is, so I will start with the molecular structure, bonding and molecular structure, and with the MO diagram, we can go from the MO diagram to aromaticity concept and explain how Huckel's 4n+2 or 4n rule of aromaticity and anti-aromaticity can be explained based on MO concept, and use the same concept for the pericyclic reaction. Hope I will be able to give some message in the at the end of 4 hours. But
I am sure that this is a very, I mean, most of the time you don't have any undergraduate textbooks covering this portion that interestingly. So it will be really useful for the students to understand the pericyclic reactions and the concepts, especially on MO based approach. So students, please don't miss it. At any cost, you should be attending this one. So it will be interesting. So officially, Dr. Biju, I thank you for these sessions on oxidation and reduction. It will be really useful, not only for the students, for us teachers also. So it was a wonderful session. Thank you.
Thank you, sir. Sorry, I was not able to join on Google Meet earlier. I was following through YouTube, however. Didn't feel like missing it because chemistry presented, organic chemistry especially presented in a comparative ways new to me. Normally, you just see one reagent and a lot of reactions under it. So when you get a comparative feel, you get to know the difference.
No, if we pump in 1 hour with several reactions,
yes,
students will hear, but at the end of the 1 hour, nothing will be there.
All go above their heads.
Yeah, that's what I feel. But yeah, I hope if they listen to the presentation followed by, if they get the slides, probably many things will be there in their mind.
Yeah, slides would make it more.
And also we look forward to that asymmetric, at least some part of research work, how we are carrying out for new things. So that is later. At some later stage, we will definitely invite you to the department for students to interact. How can you get this? What is your asymmetric catalyst and things? Bit of research. So we'll do some other session, not in this, of course. But we are happy to hear from you more about that.
Sure. Anytime.
Yeah. Thank you very much.
Thank you, sir.
So let's disperse for the day.
Yeah. So okay, see you next week.
Okay, all right.
Yeah.
All right. Thank you.
Yeah. Goodbye.